For those of you who haven't figured this out yet, I'm not Chris Moore, who was supposed to introduce Dana today. Due to a family emergency, unfortunately, he couldn't come. My name is Andrea Risha, and I'll have the pleasure of introducing Dana Randall for her talk today. Dana is the co-executive director of the Institute for Data Engineering and Science at Georgia Tech. She's the advanced professor in the College of Computing and adjunct professor of mathematics at Georgia Tech also. She got her PhD in computer science from Berkeley, undergrad degree from Harvard in mathematics, and has held postdocs at IIS, DIMAX in Princeton. Her research lies primarily in theoretical computer science, focusing on randomized algorithms and stochastic processes at the interface of computer science, discrete probability, and statistical physics. Dana has many awards and recognitions. She's a fellow of the AMS, a National Associate of the National Academies, and was a Sloan Foundation Fellow, a Kavli Fellow, and a recipient of the NSF Career Award. She has also won numerous teaching, research, and service awards, and was recently the director of the Algorithms and Random Center at Georgia Tech. As the advanced professor of computing, she actually promotes women in mathematics and computer science at Georgia Tech and externally. Of course, she's a very well-accomplished researcher and has many awards. For me, the best quality that Dana has is that she is an amazing collaborator. I've been working with her in the past 2 years, and it's been just phenomenal for me, and I hope for her as well. I am in computer science also, but mostly in distributed computing and algorithms, and I know it's all computer science, it's all the same. But even within computer science, sometimes it's hard to speak the language of fields that are close, but not exactly, kind of the same, but not exactly. And we managed to bridge this barrier, and I think for me has been super exciting work, and as I said, with a fantastic collaborator. With that, I'll leave it to Randa to Dana and her talk on emergent phenomena in random structures and algorithms. Thank you.
Well, thank you, Andrea. It's mutual. And thank you all for coming. I'm really delighted to have this opportunity to address you and talk to you about some research that I've found exciting. And I especially thank the AMS and the committee for this opportunity. So the title is a little bit weird. People have said to me, emergent phenomena doesn't really tell anyone what you're talking about. So I'm going to start with just a definition of what I mean. So emergent phenomena are going to be characterizing some phase transition in a state space. So phase transition is just a macroscopic change in some observable due to a microscopic change in some parameter. And that's going to be the theme that comes up throughout all of the examples that I talk about across several different fields. So we know it commonly as water turning to ice, something becoming magnetized. This is exactly the type of phase transition that I'll be talking about. So I'm going to start with just examples, all right? And the key thing is that when you're on one side of the phase transition, there's usually some defining characteristic, some observable at the macro scale that describes what happens on one side that isn't present on the other side. So, these examples are really from all over the place. They might look very different, and hopefully by the end of the talk, I'll convince you that they're very similar. So the first is demographic data. So this is data from a website that talks about in various areas, the most prominent race of a given area. So those of you who are from the area probably recognize this as New York City. This is where I grew up, where the star is, which is in fact a predominantly Asian area. If you look just south of the star, you'll see a little blue area that is a predominantly white area. That's where Trump is from. Okay, so just the fact that you get these clusters of colors, there's lots of different ways to explain it. I'll show you a theoretical model that tries to justify it as well later on. Cooperative behavior in nature. I could have taken many different examples. I chose these 4 because I will be saying something about analysis of these later on. But it's just you see animals in nature, they collect, they form some as a community, they do something together. It's not clear how they're communicating. And you get some emergent behavior. So it might be that you have these organisms that collect in a small colony that's tight-knit. You have ants bridge, so they actually walk on each other to form rafts or to connect to land masses. Alignment, this is sort of a weird picture, but I really just mean flocking. So you have a bunch of organisms that all of a sudden collectively start going in the same direction. How does that happen? Locomotion is very different because there's nothing collective. That is a single organism. I'll talk about it later on. But if you look inside it, there's sort of cooperative behavior going on at the cellular level. And we'll see that it's a similar phenomenon. Okay, so these are the examples that usually when I talk to audiences in computer science, they're more excited about, and then I go to the math example and everyone goes, oh, but I'm assuming that in this audience you want something more tangible than mathematical. So I'm gonna start by really explaining how phase transitions happen, hopefully not in too much detail, but this is called the hardcore lattice gas model. So I give you some underlying graph, a finite graph. In this case, it's a region on the Cartesian lattice. And I'm going to look at subsets of vertices with the condition that no two vertices can ever share an edge. Okay, so this forms an independent set. In the language of discrete math, it's the hardcore model from physics. And I'm going to give it a weight. So I have a parameter lambda, which is called the fugacity or activity. It's just a single parameter that the weight of any independent set is lambda raised to the size of the independent set, okay? And then I'm dividing by z to normalize this and make it into a probability distribution, okay? So z is just the sum over all configurations. And now that means that if lambda is equal to 1, I have the uniform distribution over all independent sets. And when lambda is less than 1, my distribution is favoring sparse independent sets. And when lambda is greater than 1, I'm favoring dense independent sets, okay? And this is what happens when you change lambda a little bit. I say smaller and larger because I'm really not changing lambda very much here. If lambda were truly small, I would have a very sparse independent set. But in this very small neighborhood, you see a dramatic difference by just tweaking lambda a little bit. So on the left, if you look at a typical configuration for this value of lambda, you see about the same number of red and blue vertices, where the blue vertices are the even sublattice. So these are the vertices on the Cartesian lattice the parity of the sum of their coordinates is even, and the red sublattice is the one where the parity is odd, okay? So when lambda is below a certain point, a typical configuration will be about half and half red and blue. And when lambda gets larger, suddenly a typical configuration is predominantly red or predominantly blue. So you see a dramatic change in this order parameter, okay? And this is indicating that there's some phase change going on, okay? So my talk is going to be talking about things that hit on all of the examples that I just gave you. It's 3 different communities looking at problems that are actually quite similar. So the first is sort of traditional statistical physics or discrete probability, where people are looking to understand limiting distributions, thermodynamic properties of large physical systems. We'll be talking about Gibbs states, and I'll define that in a minute. So this is sort of more the mathematical point of view. The second thrust is going to be in computer science, where we're trying to come up with algorithms to model these various systems. And we're going to use Markov chains, so various kinds of randomized algorithms for sampling. And we're going to see that the algorithms themselves undergo a phase transition. Okay, so the algorithms will be efficient and usable up to a given point, and then they become prohibitively slow. Okay? And the third thrust is this more recent work that I've been doing with Andrea and others, and I'll talk about it at the end of the talk, which is harnessing emergent phenomena. So what I mean by that is the kind of collective behavior that I was showing you about flocking or compressing or what have you, rather than to try to understand it, maybe it is just one of these things that comes out of these phase changes where all of a sudden you see some macroscopic change. Maybe we can harness that to design algorithms that sort of mimic this behavior, and we can use that. And we're trying to look at how it could be used for what's called swarm robotics or for programmable active matter. So these are things that I know very little about, but we will get there, and you'll see why these things are all related. Okay, so starting with understanding emergent phenomena, I explained the hardcore model on a finite graph, but really we're interested in what happens on the infinite graph. So how do you define a measure on the infinite graph? Is you want to somehow take limits, okay? So what we're going to do is consider successively larger finite regions where we hardwire some configuration on the boundary. That's going to disappear when we go to the limit. And we're going to look at some fixed box on the inside, say an n by n box. So this white box stays fixed, and the outer thing is going to get larger and larger. And we look at the conditional probability on the white box in the middle, and we try to see if there's a unique limiting distribution. Okay? So there's a very strong conjecture from statistical physics that says that there is a critical point here. They believe it's around 3.79, so this has been studied quite extensively, that says that when lambda is smaller than lambda c, the critical point, you will have a unique limiting distribution, while when you're larger than lambda c, you will have multiple limiting distributions called Gibbs states. Okay? So this is the picture that you should keep in mind. So the top two are what happens when lambda is small. You have a red and a blue boundary, meaning what I'm hardwiring around the boundary is I'm including in the independent set all of the even points around the boundary or the odd points. Okay? And I want to know if this is going to affect what I see inside that middle square that's staying fixed. Okay? So I'm taking larger and larger regions, and the conjecture is that below a certain critical point, what you see in this inside square is the same in both cases. And then you hit a critical point where there's some long-range influence that persists no matter how large the outer one gets. So with the blue boundary, you would expect to see more blue vertices, and with the red, you would expect to see more red, and you can see that the limiting distributions will be different. Okay? So Dobrushin, who initially studied this idea in statistical physics, he was able to prove that if there is a critical point, lambda c, we still don't know that one exists, but if there's a critical lambda which has this behavior, it's larger than a quarter, and it's less than some large constant that Christian Borgs and David Galvin have worked out, and it comes out to about 300. Okay? So they proved this. What they really proved is that when lambda is less than a quarter, you have uniqueness. When lambda is greater than 300, you have non-uniqueness. So if there's a change, it's going to happen in between those two. Okay? And a lot of us have been working on trying to understand this still, and those numbers are coming together. So there's still a gap, but now the upper and lower bounds on lambda c, if it exists, are within a factor of 2. Okay, so we're in the ballpark. And I will, there's two different results, one for the lower bound and one for the upper bound, and I'll be talking about the upper bound more later. Okay, so for the upper bound, which is showing you that lambda c, the critical point, is less than 5.35. This is the best that's currently known. That box is just a ... okay? That just got changed. So really what I'm trying to show you is that if lambda is larger than this value, we have multiple Gibbs states. Okay, so I want to show that the boundary conditions persist. And the way you would try to prove this is by identifying any event where you could show that the probability of this event is different in those two scenarios, when you have the blue boundary or the red boundary. So the most common one that people look at is look at the origin, which is an even point, and is that more likely to be in the independent set when the boundary is blue, so it's consistent, or is it more likely to be in the independent set when the boundary is red, and this is an inconsistent color? Okay, so I mean, both are possible for sure, but is there a difference, a significant difference in these two probabilities that we know will persist even as the lattice gets bigger? So this is how the proofs usually go, but this distinguishing event that distinguishes these two boundaries can be anything we want. And here's a different distinguishing event which might convince you a little bit more easily that when lambda is large, there's a difference. Whoops. Okay, so let's take the entire square and say, what is the probability that all of the even points inside the square are in the independent set? It's exponentially small, but it's exponentially smaller. So it's exponentially small in both cases, but it's significantly smaller in the left case than in the right case when lambda is large. Okay? So this seems like an easier thing to try to show, and that would be enough to show that there are multiple limiting distributions. So I'm just going to give you a flavor of how this proof goes. Let's take the configuration on the left that we want to understand has ridiculously small probability. Okay? So we're just going to look and think about what's really going on if I zoom in on that left picture. So in the center, I have a square where all of the even vertices are in the independent set. On the boundary, I have all the odd points in the independent set. So there has to be a contour that separates these two. Okay? And in particular, because red and blue can't be right next to each other in the independent set, there has to be some contour of empty space. Okay? So I identify that larger sort of rounded square, which it goes around that whole square. And I'm going to observe that if there's empty space, that entire larger configuration, I can shift one to the left. There's space for me to do that. And if I do that transformation, it opens up space, and I could add a lot more vertices to the independent set. And if I add those vertices, remember, that was an n by n square, so I could add n vertices. I've increased the weight of the image by lambda to the n. So I've increased it exponentially. Okay, so that seems to give some indication that what I have on the left with the red boundary and the blue square is significantly less likely than if I had the blue boundary and the blue square. Okay, so we do have this contour. I just drew it as a cartoon, but if you look carefully at what these contours really are, they're minimal, unoccupied edge. It's an edge cut set that is connected, and the square is on the inside. The boundary is on the outside. There's various defining characteristics. The length of the contour has to be at least 4n because it includes the square, which is an n by n square. Okay, so it's even larger. And so it turns out that the length of a contour has to be a multiple of 4. It's a fun exercise. So we have this length 4L contour. If we shift it in any one of the directions, it opens up exactly L places that a new vertex could be added to the independent set. It's another fun exercise. It's a little surprising at first. Okay, so that means that we're mapping from a configuration to a new configuration which has significantly more weight, but it's not an injection. It's a many-to-one, it's a one-to-many mapping. So if I look at the image of that map, there are many pre-images where the original configuration could have come from, and I have to bound how many. So I could undo this map if I were told where that original contour was, because after I do the shifting, I'm going to lose that information. But if I were to tell you where that contour was, you'd be able to undo this. Okay? So the measure with the red boundary of having all of S in the independent set is the sum over all contours with length at least n of the number of contours of length L divided by 1 plus lambda raised to the L. So why 1 plus lambda? So I could put just lambda to the L there, or I could be a little bit more clever and realize for all the places where a vertex could be added, I could decide to add or not add that vertex, okay? So this is the generating function that will give me all the combinations of putting the vertex in or not. If I put it in, it's with weight lambda, and if I don't, it's with weight 1. So it's a trick to just get a little bit, do a little bit better. So I need to know how many contours there are of length L. Well, if you look at what a contour looks like, these diagonal lines are bisecting the edges that define the contour. Okay, so these are edges that are separating the blue vertices in the interior that are in the independent set from the blue vertices in the exterior that are in the independent set. You have to look at it closely. I don't expect this to make sense right now, but you get some closed shape in the rotated Cartesian lattice, and it's just a self-avoiding walk or a self-avoiding loop. Okay? And we know a lot about self-avoiding walks. In fact, a really trivial bound on the number of self-avoiding walks of length L is 3 to the L minus 1. So 4 times 3 to the L. You know, you start somewhere, and then you have 3 different places to go in general because you've come from somewhere, and you can't go back there if you're self-avoiding. Okay? So with this really trivial bound, plugging it in, I get I guess my laser thing isn't going to work, but this tells me that when lambda is at least 80, okay? So when lambda is at least 80, I have, part of the sum, the first part of the sum seems to have disappeared on this. I apologize for the messed up slides. We just converted it to another computer. But so this 3 to the 4n over 1 plus lambda to the n is what goes after the summation. So we're going to get a polynomial times 3 to the 4n. So when 3 to the 4th is larger, sorry, just the opposite. When 1 plus lambda is larger than 3 to the 4th, which means that lambda is greater than 80, then we get that this measure is exponentially small, which is what we wanted to show. Okay? Okay, so this isn't a really good bound yet, but if you look carefully, the set of walks that you get are actually much more than just self-avoiding walks. We define something called taxi walks to characterize what you really get. And the real observation is that with self-avoiding walks, at every point you have 3 directions you could go. If you look at these contours that arise from independent sets, there's actually 2 ways you could go, because on even number steps, you could only go left or straight. And at odd-numbered steps, you could only go right or straight. So I could encode a taxi walk with just a string of turns or straights. Okay, and there's another observation that says I can't have 2 turns in a row. These are just very simple observations. So a trivial bound now on the number of contours is just the Fibonacci sequence. Okay, so this is the generating function that gives you the Fibonacci sequence. So this would give you that the number of contours is about 1.6 to the n, and you could just improve it a little bit more, and we got it down to 1.59 to the n. And with that, if I do that same calculation that I did before, it tells me that as long as lambda is bigger than 5.35, I get non-uniqueness. Okay, so this got us all the way down to the ballpark by just being a little bit more careful about the combinatorics here. Okay. Okay, and I just want to give you just 2 other examples. I'm not going to say a lot about them, but we're showing understanding the stationary distribution just comes down to defining the right emergent phenomenon that happens after there's a phase transition, okay? So Schelling's segregation model doesn't have a phase transition the way he originally defined it, but Schelling, Nobel Prize economist, He looked at demographics in cities. So this is going back to that first picture I showed you. And he said, imagine you have houses, you have red people and blue people. And anyone who sees too many people of the other color in their neighborhood gets up and tries to move. Okay? So he sat down with nickels and dimes on the chessboard and tried to shuffle these things around to see what would happen if you kept updating according to this rule. And you get something like this picture. So you get clusters of red and clusters of blue that separate. Okay? And it's very easy to modify this. In the modern day, I think that most of us would agree a randomized model makes more sense, and one in particular where anybody can decide to up and move. You're just more likely to move if you don't like your local demographics. And Schelling had a threshold model. It says you only move if the majority is the other color, but you could just imagine I am going to be more likely to move if more of them move in. Okay, so there's many modifications, and you could show that this model undergoes some sort of phase change. Again, not a sharp transition, but where things are integrated for a while, and then all of a sudden you see this separation. Okay? And the other model that I just want to say something about quickly is colloids, and it's just interesting that this comes up in so many different places. So this is in chemistry. You have one type of molecule mixed up in a different kind of molecule, and they're just in self-avoiding arrangements. So there's no attractive force or anything, it's just things can't overlap. They have to be in separate spaces. And you increase, so these are pictures with large and small squares that each occupy the same volume, and you start increasing the density. Okay? So you go from low density, things are very well mixed up, and you hit a point where you see something where all of a sudden the large squares cluster together. So they clump together not because they're attracted to each other, but it turns out because if they're together, there's just that many more places for the little things to go. And you see this phase change. So the only reason I'm showing you these examples is to say that if I want to analyze this and I want to show that the picture on the left doesn't have some property and the picture on the right does have some property, I need to carefully define what that property is. So it's somehow a clustering property, but it's not so clear how to define it. We define the clustering property by saying there's a region, not necessarily connected, that has large area, small perimeter, and its intersection with the large guys is 1 minus epsilon, and its intersection with, and the complement has intersection epsilon with the large guys. So it's not clear that this would be the right definition, but it turns out it is, and with this definition, we're able to show that for a discrete model of colloids, there will be no clustering at low density, and then you will get clustering at high density. And this was with work I did with former students Sarah Miracle and Amanda Stribe. Okay, so moving on to the second theme, coping with emergent phenomena, where I want to talk about randomized algorithms and Markov chains, which is really where the majority of my work has been. So here are the types of things that computer scientists look at a lot and try to sample. All right, so the first we've been talking about, I give you a finite graph, and we're looking at independent sets on that finite graph. Okay, so before I showed you the grid, but it could be any graph. The one next to it is matching, so this is a subset of the edges, so that no two edges share a vertex. Okay? The third one is from statistical physics. It's the primary model of ferromagnetism called the Ising model, where you're assigning plus or minus a spin to each vertex in the dual graph. I'm assigning it here to the squares, okay? But I get a reward every time two neighbors are the same spin, and I get a penalty every time they're different spins. And I look at the product measure. And how large that reward or penalty is parameterized by temperature. So at low temperature, I really want to have neighbors be the same, and at high temperature, I care less, okay? And you see as you lower the temperature, you go from unmagnetized, meaning about the same number of pluses and minuses, to suddenly magnetized, where you're mostly minus or mostly plus. Okay, so again, it's very similar to what we saw before. Whoops. The last one is just colorings. So this is In combinatorics, we study proper colorings quite a lot. In physics, they study not necessarily proper, but colorings, and this is known as the Potts model, and it's a generalization of the Ising model, but now we want nearest neighbors to be differently colored, okay? So if I was interested in studying the thermodynamics, or if I was interested in knowing how many configurations there were, sampling is a tool I could use in a Monte Carlo algorithm in order to solve this other estimation problem. But it's also useful, the sampling is useful just to see what these configurations look like, okay? So I'm going to imagine that all of the configurations form a very large state space for my Markov chain, okay? And of course, I'm not gonna write it down because all of these have exponentially large state spaces. But so think about, I mean, another example that you're familiar with where you have an exponentially large state space is shuffling a deck of n cards. So you probably usually stick to 52, but you could easily imagine generalizing that. And okay, so you're going to start off somewhere, and you have some rules that tell you how to update your configuration so that you stay in the state space, and you keep walking. And the hope is that after not too many steps, if you say stop, and you output where you currently are, that it's a good estimation of the overall distribution. Okay, so that's what we're hoping will happen. So if you wanted to design a useful Markov chain, you have 3 steps. You need to come up with moves that connect the state space, so you have to convince yourself you really can get everywhere. You need to define these transitions in such a way that the limiting distribution will be useful. So that might sound hard, but it really isn't typically, and the Metropolis algorithm is a standard algorithm that tells you how to define these probabilities to converge to the desirable distribution. And the last step that you have to do is convince yourself that it happens quickly, or determine it doesn't. You want an algorithm where this happens quickly, okay? So the first 2 are typically very easy to accomplish, and the last one is really where a lot of the work goes on. Okay, so let's go back to independent sets. How would I sample independent sets? This algorithm is known as Glauber dynamics. It's local, and I'm just gonna change one vertex at a time. So I choose a vertex, and I decide to add it or take it out of the independent set. So I have a bit B, which tells me which way I'm trying to go. If I try to remove it and it's in the independent set, I take it out, but I do it with probability, which is the minimum of 1 and lambda inverse, okay? If it's not in the independent set and my coin flip says to try to add it, then I add it with probability, which is the minimum of 1 and lambda, if I can add it and still have an independent set, okay? And otherwise I do nothing, okay? So first of all, it's easy to see that this chain connects all independent sets because I start with 1 and I could just take out all of the vertices to get to the empty independent set. So the state space is connected. It's a simple proof using reversibility and detailed balance to convince yourself that this will converge to the correct distribution, namely the one I defined at the top of the slide. Okay, and so I want to know if this happens quickly or not. So I want to know how long. Okay, so the measure that I'm going to use is called the mixing time. So the mixing time is the amount of time so that the distribution that I am currently at with the worst starting point is within epsilon variation distance of the goal limiting distribution, the stationary distribution, where total variation distance, you should think of it's just half of the L1 distance between these 2 vectors, okay? And I say that a chain is polynomially mixing if it takes polynomial time in n is the size of the underlying graph that I'm trying to sample these things on. So I say it's polynomially mixing. It's sometimes called rapidly mixing in the field. If it's polynomial in n and 1 over epsilon, and we say that it's slowly mixing if it takes exponential time to get within epsilon of stationarity. So if it takes exponential time, it means you're going to have to walk for an exponential time, and that's going to be prohibitively long, okay? So to bound the mixing time, there's all sorts of you'll learn in probability theory that it's the difference between the dominant two eigenvalues that controls the rate of convergence. The largest eigenvalue is 1 because it's a stochastic matrix. So we want to look at the difference between 1 and the second largest eigenvalue. And the spectral gap, which is that difference, is basically 1 over the mixing time. So they're inversely related. It's not useful to think of it this way, though, because this is an exponentially large state space. You can't even write down the transition matrix, so you certainly can't calculate eigenvalues. So we've invented lots of methods to try to approximate this. Conductance, flows, coupling, isoperimetric inequalities, and these are all methods that we've been using to infer bounds on the spectral gap. And so, for example, the easiest one when it works is to use a coupling. And if you use a coupling on that independent set model, the hardcore model, you would find that when lambda is less than 1/2, we have polynomial mixing. So this chain converges quickly when lambda is super small, okay? And then there's many other improvements that have happened over the years. Here's some of them. So over the years, this continually gets improved. The last result is Sinclair et al. Recently got lambda up to 2.538, okay? So we're getting better and better values. So in that whole range, we know this chain will converge quickly. So this is very promising. Unfortunately, there are complementary results. So we also know that this chain will take exponential time if lambda is too large, okay? So we've brought that down, and you might recognize this 5.35 that I showed you previously when we were talking about Gibbs states. It's the same value. The proofs are slightly different, but very similar to each other. And so this is work that I did with Blanca, Chen, Galvin, and Teteli. Okay, so we have the best bound and, so far the upper bound, but these are getting within the same range. And for the Markov chain algorithm, there's a very similar conjecture, which says there's a critical point, and this algorithm should be convergent polynomial time up to some critical point, and then an exponential time. And wow, the critical point is 3.79 again, not coincidentally. Okay, so we believe that's the same picture, but we only understand it outside of that gap. Okay, so we understand it away from the critical point. So this is why you should expect that that's a reasonable thing to believe. Here are 3 independent sets, all right, just 3 particular ones, the all blue, the all red, and 1 half and half. The thing to notice is that the all blue has n squared over 2 vertices, as does the all red. The one in the middle that's balanced has to have fewer vertices. So it only has, at most, n squared over 2 minus n over 2 vertices. You have to take some out in order to make it half and half. So you expect that you're going to have this bimodal distribution if you look at the free energy, if you're looking at how red or how blue a typical configuration is. Okay? So these single vertices, one on the blue side and one on the red side, have exponentially more weight than any balanced configuration, okay? I'm cheating a little bit because the middle configuration has exponentially smaller weight, but there's exponentially many of them. So I have to consider those 2 trade-offs to convince myself that we really have this kind of bimodal distribution. And that's where all the work is, okay? But if this is the picture, then when lambda is large, we have a bad cut, which means there's a bottleneck in the state space, and it will take exponential time to go from the left side over to the right side, which tells you you need exponential time to converge. Okay? I will just quickly say that the key to the proof here is realizing that this picture where you have a bimodal distribution is one way of slicing up the state space. There's many others. So what we're trying to show is that this cut set in the middle has small probability, and there's a combinatorial way to partition the state space into crosses and fault lines. So I'm going to just claim, without saying much, that every independent set either has a red cross, which is a set of red vertices that go left to right and top to bottom, or it has a blue cross, which is a set of blue vertices that connect left to right and top to bottom, or it has a fault line, which is an empty path from the top to the bottom or from the left to the right that is empty of vertices. So it has to have one of these three things. Okay, there could be one little error, but I'm not going to say anything about that. And to transition from a red cross to a blue cross, you have to go through something with a fault line. And fault lines are now long. So we, just like they were in the case that we had that big square, and they're taxi walks. So we get the same result that we had before. So we had to use a different defining property for this middle set, but once you find it, the proof follows very similarly. Okay, so mixing times for local algorithms, we see that we have this phase change. It's not necessarily a sharp change for independent sets that we've been talking about. For the Ising model, we do know there's a sharp critical point. We know that it's fast when, yeah, so my symbols changed, but when lambda is less than or equal to the critical point, we have fast mixing. When lambda is greater than the critical point, we have exponentially slow mixing. This was a long series of results, and I'm not crediting everyone, but Lubetsky and Sly most recently, I really nailed down that it's fast at the critical point, which is quite amazing. So this is fully analyzed. For colorings, you get the same thing, but there's no parameter. So the way you see the phase change is by increasing the dimension. So in 3 dimensions, we know local algorithms are fast. In very high dimensions, we know they're slow. Okay, so that was a series of, the slow results are fairly recent. And I just want to say that sometimes it suggests new algorithms to use, okay, which is very promising. Okay, so now I want to get onto this last part, which is sort of fun, which is how we could harness phase transitions in order to build distributed algorithms that could be used in various areas of computer science. Okay, so programmable active matter says, how can we get a set of interacting particles to accomplish some specific task? And the 4 tasks I'm going to look at are the ones I showed you at the beginning. So this is used in swarm robotics. This is an example of kilobots, which I've always wanted to say in a big talk. It's just such a silly term. In DNA self-computing, self-assembly. And smarticles is what our collaborator Dan Goldman has been working on at Georgia Tech, which are these little robotic elements that interact, and I'll talk about that in a second. Okay, and so we're going to model these by self-organizing particle systems. They have constant memory, and they're fully distributed local algorithms, which means each particle knows nothing global. It sees who its neighbors are. It has constant memory, and it has to make a decision whether to move or what to do. And we're trying to get them collectively to do something interesting. Here are the interesting things we want them to do. Okay, so for compression, can we use these local distributed rules to get a connected set of particles to compress in the way you would expect to see a colony kind of in some local area? Okay, so we say that a configuration is alpha compressed if the current perimeter is within an alpha factor of the minimal possible perimeter. So the first configuration is elongated, it's not compressed, the second one is. And our algorithm is just going to do Metropolis, a stochastic process where each particle looks at its neighbors and decides where it could move. The rules are very complicated because we have to make sure that it stays, that it in a distributed way stays connected, so it's a little bit complicated, but they're just making little local decisions, and we're favoring more things touching each other. Okay, so we're favoring, if it moves to a place that has more neighbors, it's more likely to do that. And when lambda is equal to 4, you could see the progression, and you could see how this thing is compressing. Okay, so we were able to prove that you get compression in this case. When lambda is equal to 2, you don't get compression. So it's interesting, because lambda is larger than 1, but we're still not getting that desired behavior. And we were able to prove that When you're less than 2.17, you won't, and when you're larger than 2 plus root 2, you will. These are very similar proofs to what we've seen before, so we can get these things to collectively compress. Okay, I'm just going to talk, I know I'm out of time, I'm just going to show you cool things about these other 3 examples. I'm going to skip bridging, although it is sort of fun to see how the ants actually go across this gap. So we have a model based on compression that allows us to simulate this. Alignment. Okay, so this was where we were trying to get things to flock in the same direction. We have a model where we have blue vertical diamonds and red horizontal diamonds. I'm going to let you in on the secret. Okay, so it's not obvious when you see the configuration, the simulation at first, but these are just the blue sublattice and the red sublattice we've been talking about from independent sets, but it's disguised, okay? So it's disguised in such a way that if I simulate both of these, oh God. Okay. This is supposed to go. Why isn't it going? Okay. You get that type of configuration, and if you, this isn't my computer, which is why I'm having a hard time. If you simulate it a little bit larger, you see that alignment happening. This is just running an independent set algorithm, but we did it in such a way that the physicists were kind of blown away that it actually worked, so which was sort of fun. Okay, locomotion. This one is a little bit farther from something we could actually say something algorithmic about, but this is euglena. It's a small organism. It has a flagella. It's a flagellate, but it doesn't use its flagella to actually move. It moves by sloshing around inside, like you're seeing, okay? So we were sort of motivated by this. On the right, I'm showing you the gadgets that Dan Goldman builds in his lab. So these are, they look like staples, and he could blow a whistle and they start moving their arms. This is all they can do. We call these smart. So these are his smart particles or smarticles. You put one of them on the table and you blow the whistle and it just goes like this. It doesn't move, okay? It's on the table. But then he takes about 5 of them, puts them in a ring, and they start jostling into each other. So he blows a whistle and they all start moving, and you start to see this thing begin to move. And if you do an analysis, you see that it's Brownian motion, okay? But then what we did is we said, what happens if you kill one of them? So all of them are moving their arms except one. One of them is just staying like this. And suddenly you get Brownian motion in the direction of the dead guy, okay? So that's what I'm about to show you, okay? So on the bottom, you see what a single one does. It's not particularly interesting. On the top, you were seeing Brownian motion at first, but now we have that dead guy, and you start getting Brownian motion with drift towards the inactive one, on average. If we did more simulations, it would be off a little bit, but in general, you're going to see that kind of drift, okay? So, you know, our group has been looking at, there's been a very interesting back and forth between the algorithm side, which is Andrea's group looking at distributed algorithms and my group looking at stochastic algorithms and figuring out how to satisfy the requirements of both of these at the same time, which has not been easy in most cases. But for this, we're able to get mathematical models that simulate compression and so forth. I'm gonna just go past this because it's really distracting. But before I say the conclusions, I want to tell you why we think this is sort of an interesting direction. But you know, so the two of us are working on algorithms. Dan is actually working on whatever we come up with, he's trying to build. So the way we made this one guy die is we made them photosensitive. So if you shine a light, whichever smarticle sees the light freezes. So if you shine the light in different places, you can get this collective thing to move in certain directions. So you should think of it as, you know, when people build swarm robotics, they take really smart robots and they put them together to get some large thing happening together, but you hope that they don't do anything too stupid. So they take these very expensive elements and they try to get something to happen. And we're taking the opposite approach, which is let's take really, really dumb robots and see if we can get them collectively to do something a little bit smarter, okay? But on the algorithmic side, we have this very simple algorithm now for compression and for expansion. Okay? So here's how you might want to think about using this in a programmable way for more complicated tasks. Imagine you wanted to model foraging. Okay? So you have these particles, they're hungry, so they have a low value of lambda, and that or a large value of lambda, that causes them to compress around some food source. They all eat until they deplete the food source. Okay? And now they get hungry because the food source is depleted. So their self-regulatory system could just modify what lambda is. By lowering lambda, they collectively move. So each one individually says, I'm hungry, I'm going to lower my lambda. And suddenly you get into an expansion phase where they start looking for new food sources. Okay? So now if they identify a new food source, as they start getting fed, lambda will start going up again, and they'll compress around the new food source. Okay? So we have all sorts of scenarios where we're looking to, the whole point here is that we're trying to use the emergent phenomena to themselves just get the collective behavior without having to choreograph how all these different particles should act in this very complicated algorithm. It's uniform, and we're just telling them this will happen organically, so just let it happen. So it's been kind of fun. So my conclusion, just to sum up, I've shown you 3 different worlds. We're using phase transitions and these emergent phenomena to infer properties of these large systems, so to understand their stationary distributions. So that's more on the math and physics side. We're using it to determine when certain classes of algorithms are efficient and when they're not. And when they are efficient, we can use them in order to sample and study these state spaces even more. And last, we're trying to see how we could actually use emergent phenomena and harness them to build distributed algorithms where we think interesting things will happen, because that's exactly what happens when you have a phase transition. Interesting stuff happens. So thank you. I'm going to conclude, just say thank you. And a small advertisement that we have a special session related to this in the afternoon. So at from 1 to, we're going to end a little early because the last talk won't be there. So if you're interested in this kind of topic, we have people speaking from self-assembly, from the biological side, and from the Markov chain side. And so I'm looking forward to that. So thank you very much.
I think we may have time for 1 or 2 short questions. I see someone there already.
Hi, thanks. One quick question. So does any of this have implications for like particle swarm optimization or step size choice? Because often in these things they get stuck or...
Yeah.
So yeah, are there any applications there?
You know, potentially, like from the biological side, you know, when Dan started looking at this, he was looking at static staples and seeing how things get jammed under certain certain cases. The non-equilibrium dynamics are harder to analyze, but in simulations, there's definitely connections across these 3 areas where you see similar things to like ants all of a sudden jamming when they're trying to go into a tunnel and getting into local suboptimal configurations. Yeah, so these are examples of optimization problems where you can look at it from that perspective, but we can't analyze that.
Thanks.
Yeah.
So I have a small question. So in physics models, when you have Gibbs states, there are probability distributions and configurations. But when you do algorithms, it seems that they become dynamic, and you have to define a probability transition. So I'm kind of confused with that aspect.
That's right. In physics, we're looking typically at the infinite lattice also,
Right.
whereas in computer science, we aren't. So in both of those cases, I'm trying to identify, to infer that certain things have exponentially small probability.
I see.
So I defined I'm looking at my Markov chain only to say, is there a cut set that I have to go through with my set of moves that has exponentially small probability? And then I don't have to look at the dynamics at all.
I see.
Right? So it really is a question about the state space where I'm only saying, do my moves have to go through a bottleneck? And beyond that, the dynamics really disappear from the analysis.
I see. Yeah, thank you. Thank you.
All right, let's thank the speaker
Okay,
again.
thank you.